Welcome to Dr. Sherry's Astronomy channel. The theme this time is, Discovery of a Black Hole Growing 40 Times Faster Than the Theoretical Limit. Black holes are one of the most mysterious objects in the universe. They have extremely strong gravity, which attracts and pulls in surrounding matter and even light. As a result, anything close to a black hole is unable to escape, becoming invisible from the outside. This is why they are called black holes. There are various types of black holes, and among them, especially massive black holes are believed to play a major role in the evolution of the universe. These supermassive black holes are found at the center of galaxies, with some having masses ranging from millions to billions of times the mass of the Sun. For example, there is a large black hole at the center of our own Milky Way galaxy. Supermassive black holes, which grow alongside the evolution of the universe, are thought to influence the structure of the universe and the formation of galaxies, though many unanswered questions remain. One of the mysteries is how such massive black holes form so quickly, within just a few 100 million years after the birth of the universe. Our universe is thought to have begun around 13.8 billion years ago as a hot ball of fire, and over time, it expanded and cooled, giving rise to a variety of celestial objects. Considering the evolution of the universe, in the early stages, there were no stars or galaxies. Eventually, the first stars and galaxies formed. Therefore, black holes did not exist at the very beginning of the universe. However, in the nearby universe, there are supermassive black holes like those observed in M87. Many galaxies also have supermassive black holes at their centers, shining brightly and known as quasars. Some of these quasars are even observed from the early universe, several 100 million years after the Big Bang. Thus, the formation of such large black holes just after the Big Bang is one of the greatest mysteries of the universe. There are several theoretical models explaining how supermassive black holes form and grow. One key concept is the existence of primordial black holes, which act as seeds for the formation of supermassive black holes. This diagram shows the growth of black holes based on two primordial black hole seeds. The horizontal axis represents the mass of the black hole, while the vertical axis shows redshift, indicating the age of the universe. The further to the right, the heavier the black hole, and the higher up, the younger the universe. The diagram includes observed data and models of how black holes grow. Quasars are shown in the lower right part of the diagram. Recent observations from the James Webb Space Telescope have uncovered distant supermassive black holes. The area that the James Webb Telescope cannot observe is marked with a blue dashed line. Currently, two main scenarios are considered for the formation of primordial black holes. The first is for light seeds. This model proposes that massive stars formed in the early universe collapse at the end of their life to form black holes. However, black holes formed from stars are relatively small in mass, so it remains a mystery how they grew to such enormous sizes. The second scenario involves heavy seeds. In this case, a giant gas cloud collapses directly into a black hole, bypassing the star stage, which could lead to the formation of a massive black hole more quickly. One key process in the growth of these black holes is accretion, where the black hole pulls in surrounding material. The rate at which a black hole can accrete material has a limit, known as the Eddington limit. Several growth curves based on the Eddington limit are shown in the diagram, marked with multiples of Eddington. Normally, black holes grow within the Eddington limit, but recent studies suggest that some black holes may grow rapidly beyond this limit in a special state called super Eddington. For example, a region marked as 10 Eddington is shown in the diagram. Understanding these growth models and mechanisms is crucial to unlocking the mystery of supermassive black holes in the early universe. To investigate the mystery of these massive black holes, various observational projects are underway. One such project is the Cosmos Survey, a large-scale observational effort using multiple telescopes like the Hubble Space Telescope and Spitzer Space Telescope to observe vast regions of the universe across different wavelengths. This allows detailed study of distant galaxies and black holes from the early universe. In particular, the Chandra Cosmos Legacy Survey focuses on X-ray observations, using NASA's Chandra X-ray Observatory to explore the regions covered by the Cosmos Survey in X-rays. X-ray observations are ideal for detecting black holes and galaxies hidden by dust, revealing the presence of supermassive black holes in distant parts of the universe. One of the key discoveries from the Chandra Cosmos Legacy Survey was a black hole known as LID 568. LID 568 is extremely bright in X-rays but almost invisible in visible light and infrared, likely because it is surrounded by dust and gas, which obscures its core from normal light. To further study this hidden black hole, follow-up observations were conducted using the James Webb Space Telescope. Since the telescope can observe in infrared, it can detect celestial objects obscured by dust. The actual observations use the NOIRLab IFU mode and the mid-infrared camera MIRI. The IFU mode divides the observation area into small segments and obtains spectra from each position. While radio and X-ray observations can be done in standard modes, infrared requires special equipment. The spectra obtained from these observations look like this. The horizontal axis represents wavelength, and the vertical axis represents brightness. Green represents data from NOIRLab, while orange represents data from MIRI. Black dots show the brightness observed by the Spitzer Space Telescope. When we zoom in on the spectra obtained by both instruments, we see various emission lines, including hydrogen. These emission lines allowed researchers to measure the redshift of this object for the first time, determining it to be 3.965. This corresponds to an age of about 1.5 billion years after the Big Bang. With the redshift now measured, the object's luminosity was also determined for the first time. This graph shows black hole mass on the horizontal axis and luminosity on the vertical axis. The blue and green data points represent other distant objects with massive black holes. The newly discovered object is shown as a red star. The black dashed lines represent fractions of the Eddington limit luminosity, ranging from 0.1, to 0.01. The Eddington luminosity is the maximum brightness at which the radiation pressure from a black hole balances the gravitational pull on surrounding material. The newly identified object, shown as a red star, is over 40 times brighter than the Eddington limit. This suggests that it is rapidly growing, absorbing surrounding material and increasing in mass. Normally, when a black hole exceeds the Eddington limit, the radiation pressure overcomes gravity, blowing material away and returning the luminosity to its original value. Therefore, a special phenomenon may be at work that stabilizes the system as it grows. This phenomenon was observed in the NOIRLab IFU mode data. The images captured with IFU show the hydrogen emission lines. The three-dimensional spectroscopic feature allows creating images at any wavelength, revealing the motion of hydrogen gas based on shifts in emission line wavelengths. The team created images corresponding to gas movement speeds of 500 km per second. The left side shows gas moving toward Earth, while the right side shows gas moving away. Region C is at the center, with regions B and D moving toward Earth at speeds of 500 to 600 km per second. Regions A and C show similar velocities. These observations suggest that there is an outflow from the black hole. This strong outflow likely releases excessive energy produced during black hole growth, stabilizing the system. Furthermore, from the spread and speed of the outflow, it is estimated that the active phase of the supermassive black hole lasted about 12 million years. This duration matches the accretion time estimated from X-ray observations. Therefore, it is believed that the formation of this massive black hole was due to rapid accretion of material, not a black hole merger. This rapid accretion could explain how a relatively light primordial black hole could grow into the massive black holes we observe today. This finding helps deepen our understanding of black hole formation in the early universe and the growth of supermassive black holes. The newly discovered object may be related to a dog, dust-obscured galaxy. Dogs are galaxies whose light is blocked by dust, making them difficult to detect in visible light. These galaxies are active in star formation, and it is suggested that supermassive black holes are rapidly growing in them. Thus, it is possible that dogs harbor rapidly growing black holes, and studying these objects may hold the key to understanding black hole growth and galaxy formation in the early universe. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.